Hi, sir. I'm good, thank you. How are you?
Very good, very good. So, did you get some time to work on mechanics?
Yes, I did. Was working through a couple of the questions, and the principle that you taught me yesterday all applied. So it was actually nice and easy for me.
That's
I
very
haven't
good.
finished all of them yet, but just working through it. But I think I got the general concept.
That's excellent. So, in today's lesson, what I'll do is take three examples, which are actually common examples for the situation where forces are applied to a system and we have equilibrium position,
Okay.
or we could have a position where the equilibrium state is not there. In that case, there'll be an acceleration.
Mm-hmm.
Now, when external force is there, external force is not equal to zero, but there is a net force. In that case, the object is going to move with the acceleration. And that is where the second law of Newton applies.
All
And
right.
so we'll take up examples based on second law of Newton today. Okay?
Okay.
Let
Yep.
me share with you the screen and then we'll discuss more about it. So, Amy, as I was saying, we'll discuss applications based on Newton's second law of motion. So, here are three very common examples which are always seen. One, I'll treat this as my example number one, where we have two mass on a table. We'll
Mm-hmm.
assume that the coefficient of friction is kind of negligible between the masses and the table.
Yep.
Now, when we have a system, there could be two masses or n number of masses, but they are all on a table and they are attached by a string. That is one thing. Second case could be that we have a pulley on the side, as you can see here, and one of the mass is hanging, right? So there is a gravitational force which pulls it down, and that will set the system in motion, right? So there is
Yeah.
external forces because of gravity. In the first case, we actually apply an external force, which I have mentioned as f of p, fp. External force is applied to pull it, and then we have an acceleration. So that is how the system will be in a constant acceleration. Now, and in the third case, we'll take example where we'll take up a pulley, right? So in a pulley, we can have two masses attached to a string, and these two masses being of different mass. In that case, they will exert different force, and there will be a motion. Greater the mass, it will pull more, and then it will move the whole system with some acceleration. So in all these three cases, they are kind of related, as you can see. In first case, we are applying an external force. In the second case, the external force is applied, and that is because of the gravity. And
Yeah.
in the third case, we do have differences mass and it's a pulley system, which works. Most of the examples in your book are actually based on these three examples. There could be some
All
variation.
right.
Yeah. Once you understand all these concepts, it'll be very easy for you to actually sail through this section. And
Oh,
then we'll move forward. Okay. We'll talk about Newton's second law of motion. We'll cover these topics as a part of solution of our question, which is also mentioned here. We'll state what the Newton's second law is, how is mass and acceleration related. It actually defines them. What are the units of force? That is also very
mhm.
interesting. And how are they related? Some assumptions. Many questions, we have a string pulling the objects, right? We have a pulley and things like that. So in all these problems, so we have to draw a force diagram. And in that diagram, what should be the assumptions, right? That is very important to understand.
All right.
And then we will actually
Mhm.
take up the example and solve this particular question. So Abby, can you please read this question here?
Yeah. Two boxes with mass of 12 kilograms and 10 kg are resting on a table. The horizontal force of 40 newtons is applied by a person to the 10 kg box, as shown in the figure. Find the acceleration of each box and find the tension in the cord.
Correct. So that's the type of question. Rather, this is the question which we are going to solve in this particular video. But before that, we'll understand all these concepts. Now, a few important things is when you see the units, like 12.0 kg, 10.0, and 40.0, it clearly indicates that we are talking about three significant figures. So if nothing is mentioned you have to write your answer to three significant figures. Is that clear to you?
Okay.
So at
Yeah.
this level, many times you're in the test paper, your teacher may not write the answer to three significant figures, but looking at the question itself, you should decide what should be this number of significant figures for this particular question. Okay,
Mm.
right.
Yeah.
Now, since this is mathematics and not physics, we'll kind of dilute it. But if this would have been a physics lesson, in that case, you have to be very precise. Okay,
All right. Yeah.
perfect. You can also extend this question. That is to say, I'm only taking two masses, right? I'm taking mass 1 and mass 2. However, in this question, we could have many other objects, masses in between, similar to these. Think about
Mhm.
a train going with a lot of bogies with it, right? Many compartments, right? So engine is
Mhm.
pulling them up, and we have, let's say, 10, 20 of those rails with it, right? So in that case, we can actually adopt the same method. You can think that M2 is all rest of the boxes. You get my point. M2
All right.
is
Okay.
rest of the boxes. You get the idea. So
Mhm.
even if there are 10
Yeah.
boxes in this kind of a situation, since we are applying the concepts of vectors, when we say mass, we are assuming that to be concentrated at a point which is right at the center, correct?
Mhm.
If there
Yeah.
are many objects, we can treat all that box as one box, correct? And we can call that as
Yeah. Yeah.
M2. We can call that as M2. And then solve this
Yeah.
question in a very similar fashion. You understand the idea.
Oh. Yeah.
Now that
Yeah.
makes
That's
it
clear.
extremely flexible. So if in your test paper, instead of two, there are three boxes or 10 boxes, you can still adopt the same method and get the solution. Is that clear to you?
Oh, right. Okay. Yeah.
Now, nothing has been mentioned about the friction. So we'll assume that the surface is like there is no friction between the box and the surface.
Mm.
We'll
Okay.
assume that
So
also.
unless they state otherwise, then you just assume there's no friction.
Yes. And so there are,
Oh.
as you can realize now, with every question, there are a lot of assumptions which you need to write down sometimes in the test paper also. That could be a part
Mhm.
of your question. What are the assumptions based on which you got this solution? Does it make sense to you?
Yeah.
Correct.
Yeah.
Be open, and like these are the important things which sometimes students miss out, and they lose a lot of marks because solving a question could be 5 marks, but all other things could also be 5 marks, right?
Right.
So
Yeah.
this is very important to understand. So let's begin with what second law is exactly. Okay, so Emmy, second law I've kind of stated here, so I'd like you to read what is written here.
The acceleration of an object is directly proportional to the net force acting on it and is inversely proportional to its mass. The direction of acceleration is in the direction of the net force acting on the object.
Correct. So acceleration A, net force is sum of all the forces acting at a point, right? So at that point,
Mhm.
all the forces. That really means that if I am going to draw any diagram, in that case, all the arrows which I am drawing, they will be originating from one particular point only. You get my idea, right?
All right. Yeah.
This is very important, right? So at this particular
Mhm.
point, we are just adding all the forces and we are calling that as the net force. The statement
Okay.
which I have given you here is not exactly second law of Newton, but it is kind of an explanation of that. So I'd like you to write down Newton's second law from your notebook, word to word. So when they say state Newton's second law of motion, you have to write exactly what is stated in your book. Is that clear to you?
Oh, right. Okay.
Now, what
Yeah.
does it really implies? That is what I've written here. Right? So don't go with
Mhm.
that topic. I just wrote Newton's second law, but realized, well, I'm actually because I'm solving mathematics paper, not physics paper. Correct. So that's the whole idea, right?
Right.
So we'll deviate, as
Yeah.
I was saying right in the beginning, many ways, right? So it is not a solution to a physics student. Okay, it's for the mechanics,
Mhm.
mathematics, GCSE, right?
Yeah.
Let's be clear about it. So the acceleration
Yeah.
here is sum of forces divided by inversely proportional to the mass. You can
Mhm.
rearrange this particular equation and say, well, the sum of forces is equal to ma. Now, what it really means is that from the diagram shown, let us say that these two forces are equal, right? It doesn't look like, but let us say these
Yeah.
two forces are equal. That means the object is
Yeah.
not going up or down, right? So we can say force up equals to force down. Then there is no movement up
Mhm.
or down, correct? Now, let's say this force F1 and this is the force F2, right? And let us assume that F1 is greater than F2, right?
Okay.
In that case, there is a net force. We'll call this force as Fn, which is in right direction because F1 is pulling to the right, F2 is pulling to the left.
Right.
If there is a net force, then the object will move, correct?
Oh, yeah. Okay.
Well, if suppose F1 is equal to F2, then acceleration is zero because net force is zero, right? Because
Right.
F2 minus F1 is zero. So if that is zero, right? So zero equals to ma, mass cannot be zero, mass is constant, right?
Right.
So acceleration is
Yeah.
zero if we're talking about equilibrium where the two forces are equal, right? So that is the case
Hmm.
which you had done earlier, where we were talking about equilibrium forces, right?
Yeah.
So in that case, acceleration is not there. But in our example, a force is applied so that there is some extra force which will move the object. And we are interested in finding the acceleration of the object, correct? That was a part of the question.
Yeah.
So now, can you please read this?
From Newton's second law, we can make a more precise definition of force as an action capable of accelerating an object.
Perfect. So force is necessary for acceleration to exist. You understand?
Oh,
That
right.
is very important. And we're talking now about a constant acceleration in this particular case, right? So when we say F equals to
Hmm.
ma, we apply a constant force, mass is constant, acceleration will also be
Right.
constant. Acceleration will
Yeah.
also be a constant in this case. You understand? So if a force of let's say 10 newtons is applied to an object and it moves, then it will move with a constant acceleration a. Correct?
Hmm.
Now let's look into the units of force. So worldwide, we use SI or MKS units. Perfect. During our time, this transition was taking place. CGS system was there and the British unit system was also there. Most
Hmm.
difficult for us while doing engineering was to work with the British units. They are like still crazy, right?
Yeah.
The world over has changed to the MKS system. However, since you are from England,
Hmm.
they have still not dropped their valuable British units. So they are still existing. And I thought, let me just give you overview of these units also before getting into details, since you might get something in British units, right?
Right.
Force in MKS or SI units is newtons. And as we said, F is MA, that means mass MKS. MKS is the units meters, kilograms, and seconds. So mass is in kilograms and acceleration is meters per second square. So 1 Newton is basically 1 kg meters per second square, correct?
Mhm.
Simple as that. When we talk about CGS, then length unit, so this is like length unit is centimeters, right? And the mass unit is grams, percent time unit is second, second square, and that is called 1 dyne. So
Oh,
dyne is a unit in CGS. Relation between dyne and Newton is since gram is 1000 and centimeter is 100th, so 1 dyne is 10 to the power of minus 5 newtons. Is that clear to you? Right?
yeah.
Divide by 1000, divide by 100, 10 to the power of minus 5. Now let's get to the British unit. So the unit is pound, right? When you buy groceries, sometimes you buy a pound of something, correct?
Yep.
So weight is a force. Weight is a force, correct?
Hmm.
So, so that is that pound unit for force. And 1 pound is, so what is the unit for mass in British unit system? Do you know that? It is
No.
called slug.
Oh, I haven't seen that before.
And
All right.
feet per second square. It is surprising, Uh, you are
Yeah,
never
I've only
going,
seen the
you're never going to
SI
drop your
units.
pounds and your units, right? After all, that's
No.
the heritage which you want to carry forward with, right?
Yeah,
Many times when
that's
I
true.
talk to students in North America, they don't even understand LB is pound, right? They say, well, I got 5 LB of this.
Yeah. Yeah, I don't really get that. But yeah,
Right.
fine.
I like you to read this statement.
One slug is the mass which will undergo an acceleration of 1 feet per second squared when a force of 1 pound is applied to it.
Very important. Now, this is very important from, some like you have some brain teasers or sometimes some competitions
Yeah,
where
yeah,
tricky questions are asked. So these are
that's true.
like things which we have forgotten about. Somebody might just ask you that. But people near you
Oh,
are more concerned with 1 kg. Can you please read
all
with what
right.
1 kg is?
Yeah, yeah. So yeah, if I ever hear now one slug, at least I know like what it is and what it's about and
Yeah.
what it is in acceleration. Yeah, yeah. Okay.
Yes. So what is 1 kg? Please
Well,
read this also.
all right. 1 kg is the mass which will undergo an acceleration of 1 meter per second squared when a force of 1 Newton is applied to it.
Be clear about. This is very important definition, and many times you need to write this. What is 1 kg?
Oh,
Is the question, right? So it is
word
not
for
just
word. Okay.
Newton's second law. There are many things into it. So while we review
Right.
this, it's good concept to understand all these things. Now, let me take
Yeah,
you to
definitely.
the assumptions which we started with. So always, whenever you have a question, you have to model this situation. And when you do that, you need to do some assumptions, right? So I'd like you to read this part. What is written there?
Okay. So when a flexible cord pulls an object, the cord is said to undergo tension, and the force it exerts on the object is the tension Ft.
Correct. So in our diagrams, we'll always have a mass which is represented by a box, and then it will be pulled by a string, which we will say cord. Now, this cord will always be, it will have some properties, right? It is always considered to be a light object in extensible string. That is the importance of the cord, correct? So, once again, when a flexible cord pulls an object, the cord is said to be under tension. It is that if I am pulling it with a force, which is, let us say, F,
Mhm.
in that case, there is a tension, and we call that force as equal and opposite force F of t. Do you see that? So when you pull,
Oh,
then F of t is the force which actually acts from the string to the object. So equal
all
and
right.
opposite force acting at this particular stage. Now, if I have to simply draw this in a particular diagram, which I'm saying is a vector diagram for representing the situation, right? Force
Yeah.
diagram, you can say. In that case, I'll represent force F in this direction and assume the mass to be at a point here, right in the center, and that becomes that point. Tails together, I will translate this force here, and I'll say this is F of t. Do you understand this portion? So this force,
Okay. So
which I am representing with F of t in this direction, will be moved. You
yeah.
can translate the vectors, right? They remain the same. Vector has
Mhm.
two parameters. One is the direction, the other one is the magnitude. So length of this arrow is the
Yeah.
magnitude, which is equal to that of the force in this particular case, and the direction is reversed. So that is how we are going to represent this particular situation. That is to say, the cord is said to be under tension. And
Wait.
yes,
Sorry. Is the force? You know when you said it's equal but opposite? Is it always equal but opposite?
yes, the
Can
tension
the
is
tension
always,
never be more?
well,
Oh, okay.
if the object is stationary, let's say it's the object stationary.
Oh.
This means if they are equal, right, that means acceleration is zero at this moment. When it
Mhm.
moves, then there
Yeah.
is an acceleration. Is it okay? So when
Yeah.
you start pulling, then there is a tension which will be same as that of the force when it is stationary.
Oh.
then there will be a
okay.
situation when the force will be greater than the tension, right? In that
Yeah,
case, it
yeah.
moves
That's
forward.
what.
Acceleration is greater than zero in that
Oh,
case. Correct? So
okay. Yeah.
try to
Yeah.
understand. So when a flexible, I'm using the word flexible cord pulls an object, the cord is said to be under tension, and the force it exerts on the object is tension Ft. So we'll just use this nomenclature. You can write T
Okay.
also. So that is the force which it exerts backwards, which is F of T. And if you make it in a diagram, it should be represented like this. All the tails at one point, and that happens to be the center of the mass. Okay?
Right.
And
Yeah.
that is how you're going to draw it. So important thing here is that chord is inextensible with negligible mass. So this chord has no mass at
Mhm.
all, and it cannot be extended. It's like fixed length. And
Yeah.
flexible chord can only pull and cannot push. So this force cannot push the object. It can only pull the object. Just
Yeah, I
keep
was gonna
it.
say.
Yes. It is just
Oh,
keeping
because
it
you said
there.
it's flexible. How can it? It can't. It will just go like that.
One
Yeah.
very
You have
important
to pull it.
basic things which we are talking about at present. We'll get to the solution soon. Don't worry about it. Now, what is a light object? Can you please read these 2 points which I've written about the light objects? Yes, please.
Yeah. So the mass of the object is negligible compared to other masses,
Light object.
and the force. Oh yeah.
Hmm.
And the force exerted at one end is transmitted undiminished to each adjacent piece of cord along the entire length to the other end. So the tension is the same at both ends of a light string.
Very important. So what we are trying to say here is that if I have another object here, and if I have similar cord attached, then this is also Ft, because the same force is transmitted to the cord if we are talking about the same
Oh.
cord. You get
So it
the
doesn't matter how many things go like connected to it, the tension will stay the
same
same.
Ft. You get the idea.
Oh,
Very important to
yeah.
understand these concepts, correct? So that is now also read what do we understand by inextensible string?
So it's a string that does not stretch,
Mm-hmm.
and the acceleration is the same in objects at both ends of a light string.
Correct. So acceleration is also same at both the ends. So if this accelerates with A, that also accelerates with A. That is important. So if my force F is more than the tension, both the objects with that string in between will actually move with exactly the same acceleration A. You understand this part now?
All
Okay.
right. Okay. Yeah.
I just added this
Mm-hmm.
point. In another video, we'll talk about system with pulleys. So can you please
Okay.
read the meaning of smooth and light pulley?
Yeah. So a pulley has no mass, and the tension is the same on either side of the pulley.
Very important to understand and difficult to understand. How can a pulley have no mass, right? Can't get it. What we
Yeah.
do
Yeah.
is such a big thing, right? So we just put a point here in the center. So we just put a peg there. Do you understand? We have put a peg there.
Yeah.
So now it has got no mass because everything is on that peg. Do you understand? The center of the mass has been nailed, and pulley is free to move. So in our examples, if it is free to move, let's say, then the mass of the pulley can be treated as negligible. You get my point? Because it has
Only because there's
it's
something in the
free to move.
center.
Yeah, it's free to move. That is how we have to
Oh.
see a pulley. And this is the string which is inextensible and supposed to be lightweight. So all
Mm.
these things are very important to understand. And then we should actually begin by solving our question. So you have a good foundation now. Do you understand all this?
Mm-hmm. Yeah. But just a quick
Yes.
thing.
Yes.
With the pulley. So let's just say something heavy was on this side, and so it goes like that.
Yeah,
So
yeah.
this is really heavy.
Yeah,
How would the tension be the same?
No.
Like on this side, on this side.
Tension will be same, direction will be reversed. See, because the tension is if the pulley is moving, now let me just draw it here, okay? So let's say this is the pulley, and as you were saying, let's say we have some object here, and
That's
let's say
heavy.
small, yeah, let's say
Yeah.
small, correct. In that case, this pulley is going to move downwards because this object is greater than the other object. Correct.
Yep.
So the tension basically will be, in this case, this will be your tension T, right? Here, the object is moving
Opposite.
up, so the tension will be T will be reverse. Acceleration is upwards. So the MA
Oh.
force will be up. Here, force is down.
Oh, I didn't think about it like that. Oh,
Tension is
okay.
now
Yeah.
pulling it down.
That's clear.
The object is going
Yeah.
to go up. Tension is going to pull it
So
down.
that's why it's the same. All
Yeah.
right. I thought the tension was going the same direction on both sides, but it's not because the force is going up here and down here. So the tension will be opposite direction.
No, no.
Yeah,
See the thing, how tension is translating. See, the tension is going in this direction. Do you see that this direction? So if you just go around this,
Yeah.
let's go around this, then tension will be in this direction. Is it okay?
Right.
So it's actually going down.
That's
Right?
clear.
Kind of same thing.
Yeah.
Pulley is a machine which helps you because there's a change in direction. It is easier to pull than to push. So when you want to draw water from the well, it helps since you are pulling it. Do you understand? So it's a machine.
Right.
Because pulling
And then it's working.
gives you that additional gravitational force, it's easier.
Yeah, yeah. All right.
It's a simple machine which translates the same force, but the direction is important.
Opposite, yeah. Oh,
When you
okay.
pull, it is easier to pull and then you can lift heavy things. But if you just want to lift it like this with the same force, it is very difficult.
Right.
You get the
Okay.
idea?
Yeah, that's
So,
clear.
Pulley is a machine which changes direction, and that makes all the difference. Okay.
Oh,
So I think you have understood
right.
all the assumptions and basic structures for mass, pulley, string, and all this. All the examples which we are going to consider where there will be constant acceleration and a constant force applied, in that case, these are the assumptions of prime importance. Okay?
Yeah.
Now let's get back to our question, which is, once again, this is the question. Two boxes with mass of 12.0 kg and 10.0 kg are resting on a table, as shown here. The horizontal force, 40 Newton, is applied by a person to the 10 kg mass, as shown in the figure. You need to find two things. One, find the acceleration of each box. We know this acceleration is going to be constant and is going to be same for each box. Find the tension in the core, F of T. So we have to find the tension in the core. That is what the question is. Now, to begin with, what are important things? First thing is you need to draw a free body diagram or a force diagram to understand the situation. Then you should be describing all your assumptions, which we discussed earlier, relate all the parameters, which will give you equations to solve, and then solve your equation. So these are the steps to be followed, correct? Whenever you're going to solve such a question. Now let us begin with drawing the free body diagram. So to draw the free body diagram, let's consider first the mass M1, right? And this mass, we are applying a force, Fp, pulling it to the right, as shown here with 40 newtons of force, right? As soon as we pull this, there will be a tension, and we are calling that tension to be F of T, right? So this is the tension which will be in the reverse direction. As I explained earlier, strictly speaking, all these lines are actually originating from the center of the body. So I'm not actually messing it up, but I'm showing you all of them are actually starting with the center of the body. And since the object is not flying up or down, the reaction is equal to the weight exerted on the table, and therefore the weight exerted is m1g, mass of the first box, and therefore that will be equal to the normal force on the first box. So many times you have to only draw I should say free body force vector diagram for an object, let's say a book on the table, correct? So that means this part only. That means we have a force which is equal to mg going downwards, and we have a reaction, you can say normal to that, which is equal and opposite. And therefore, the object is on the table. In our situation, we have an additional force applied here, and we are calling this force as F. This force is going to move, right, for sure. So the object moves with an acceleration A, right? But once it starts moving, the string will apply a tension in this particular direction, which I'm representing here, and calling that as F of T. So that is how I've made my diagram. Is this clear to you?
Yeah.
Perfect. So that is your first body, which is M1. The second, M2. If you look at this particular diagram, now this force, which is coming to this side, is exerting the same force on the second body, but it has to be in the opposite direction. It starts pulling it, right? And therefore, this is being shown on the second body, F of T. This F of T and that F of T should be of equal length. I have not drawn them, but they should have been of the equal length. They are the same forces. Because we know that the string is flexible, and therefore the same force is transmitted. So everywhere in between, the force is going to be exactly same. But now the mass is different. And therefore, the acceleration will be what? Acceleration, you know, is mass. I mean, the force and mass and relation is F equals to ma, right? So even if the force is same, right, depending on the mass, we can actually find what Ft is, will be m2 times a. Is that clear to you?
Yeah.
In this particular situation. So I think the diagram is clear to you. Is it clear to you, Anil?
Yeah, it is.
Can you please read this part, explanation on the same?
The force Fp acts on box 1. Box 1 exerts force Ft on the connecting cord, and the cord exerts an opposite but equal magnitude force Ft back on box 1.
Right. Now this part.
Since the cord is considered to be massless, then the tension on each end is the same.
Okay.
Hence, the cord exerts a force Fp on the second box, box 2. This force can only pull but not push.
It should be Ft, right? Tension. And this force can only pull, not push. Is that clear to you? That is how we get both our free body diagrams or the force diagram for the given situation. Is that clear to you? Now, as I was saying, if this M2 could be many boxes, M2 could be many boxes, right?
Right.
So same type of diagram. Okay. Now let's see, how do we solve such a question once we have made the diagram for it? Correct. So we have two boxes. Let's begin with the box number 1. So in box number 1, clearly we have Fp, which is the right side move, and Ft is the tension on the left side. Since the object is moving, we know that Fp, that is going to pull it, is greater than the tension. And therefore it moves. And from the second law, we know that that should be equals to ma. Since the mass of this first box is m1, I have written Fp minus Ft equals to m1a. Clear?
Yeah.
Very simple, right? Second box.
Yeah.
In the second box, it is the tension which is pulling it. And therefore, that tension should be equals to m2 into a. Very simple.
Yeah.
Right. Now, what
so this way you don't need to do any subtraction because the force pulling you just is the tension and there's nothing else
going on. Nothing else on the other side. So it's just getting pulled, right?
Right.
So in a train, you can think about that to be the last compartment, which is just getting pulled.
Right. Yeah.
Right. So
that's a nice way of thinking of it.
Yeah. Because that could be a question, right? So to make this very complicated, I could have, added 10 cars to it. And then what is the tension in the last car? What is the acceleration of the last car? What is the whatever, right? On the last car.
Yeah.
So that is what it is. Correct?
Yeah, that's clear.
So now, to solve this, we have two equations, two unknowns. We'll just add equation 1 and equation 2. So when you add, you realize that Ft and Ft will cancel, correct, on the left side?
Yeah.
So that is what I've done. So I have just added, and on the right side, you get m1a plus m2a. Acceleration is constant, as we have understood, right? So Fp is equal to a times m1 plus m2, correct?
Yeah.
So acceleration is, rearrange your equation. So we get our formula, which is the pulling force, which is given to us as 40 newtons divided by the sum of the masses. You get the idea. That is the acceleration. In our case, it was 40, 10, and 12. You should write with 1 decimal 0, okay, and write down your answer to 3 significant figures. 1.82 meters per second squared becomes the acceleration in this particular case. Is that clear to you?
Yeah.
So in general, you could also write this formula as whatever force you're pulling with sum of all the masses. Do you see that?
Yeah.
There could be any number of masses. It doesn't matter.
Yeah. That makes sense. And the acceleration will be constant within each box. That's the point.
You don't have to think of, if there's a multiple choice question, just divide with all the sum of masses, you get your acceleration. F is ma, right? And that's why, if you see the formula itself, we use that sigma term. You see that? We use the sigma term. It doesn't.
Yeah, I was going to say. Yeah. I was going to say with
the good convention.
You add the
here
sum.
You could add all these sum of masses, right? And get to the solution just as we got here, right? Now, we need to find Ft, right? So clearly, what is Ft? So we can always use the second equation, which directly gives us the value of Ft, the tension. M2 times A, we have already calculated the value of A as 1.82. So we'll multiply 1.82 by the mass of the second object, M2, and get the answer. So the tension is 21.8 newtons.
So do you always recommend, like, if they have questions where it's like, I think at school we said like connected particles because they're like kind of connected.
Yes.
And like you said, like with the train, the last carriage, since that has no other force acting in that direction, do you always recommend subbing, if they said find the force of the tension, do it on the last one because there'll be less forces to deal with? Or like less calculation, I mean, because like if you did it with the first equation, you've got Fp minus Ft and then it's just a bit longer.
You do like this.
Did that make any sense?
M2 to Mn, right?
Yeah.
So just take that as a block. So your system is still the same. First object and the rest of the others put in together.
Oh, okay. Yeah.
And if you're only interested in the first box, in that case, just don't bother about anything. This is sum of all the boxes.
Yeah.
F equals to MA, done. Just add all the masses together because all are together, right?
Yeah, right.
And
they're
then
all connected.
And then you get this formula. Acceleration is the force divided by the sum of masses. Do you see that part? It's good to visualize. And now you found this. They will say acceleration on the last. Well, then the last one is separately treated, and whatever the mass of Mn is, multiply this with acceleration, which you have calculated, and that gives you the tension in the last compartment.
Perfect. Yeah, that's clear.
Correct. So that is how.
Yeah. Sorry, I was just saying, like, so to find the acceleration, you just simply take the force that's being like applied and then divide it by the sum of all the masses.
Perfect.
And then if they ask for the acceleration, or no, for like maybe the tension or something for that individual box, then you just take the acceleration you calculated, times it by the mass, which will be given, and you got your tension.
You're right. You're right. So that is how we are going to do it. So for example, let me just change this question. And let's say we have 1 mass, 2 mass, 3 mass, 4 mass, right? And let's say they're all connected.
Yeah.
Right. And this is the force F, right? Let's say mass is same, right? So let's say M1, M2. They could be different. How does it matter, right? Doesn't matter.
Yeah.
Basically, you will say F equals to M1 plus M2 plus M3 plus M4 times A.
Yeah.
Let me write A in a different ink. A. So you directly get A from here. Do you see that?
Yeah.
So A is equals to F over sum of masses.
Sum of all of them. Oh, I see.
Now, if I tell you, find the tension here, find the tension at this place. Why last? It could be somewhere in between also, right?
Oh, okay. Yeah.
So at this place, let's call this as F of tension at this place. Then F of t will be equals to, we can add these two masses together, right?
Yeah.
M3 plus M4 times A. A is calculated already.
Ah, cool. Yeah.
So you could
That's
do this
nice.
at any
Okay,
place.
yeah.
You get
Right.
the idea.
Okay, yeah. But same principle applies. That's
Perfect.
nice. Okay.
That is how you're going to solve such a question. Now let's take our
Yep.
example where we have a mass and another mass is hanging from a pulley. Now, because of this hanging mass, it is under an external force due to gravity. And therefore, there is an acceleration, A. And this acceleration is same for both the masses since they are attached by a string. Correct? Can you please read this question, which we are going to
Yeah.
now answer?
All right. So two boxes with mass M1 and M2 are attached at the end of a light inextensible string. The string passes over a fixed light pulley as shown in the figure. Find general expressions for acceleration of each box and the tension in the cord.
Correct. So actually speaking, all the three examples which I have taken, they have the same statement where we will have two masses, right? And we'll try to figure out what is the acceleration of each mass and what is the tension in the cord, right? Only thing is the three
Yeah.
situations are slightly different. In the first situation, we had two masses on a table. In the second, one on the table, the other one is hanging. And in the third, both are hanging and the pulley in between. So they are very much related to one another. And therefore, our solutions, as we gradually move from one to the other, it will be very clear to you. When we add complexity to a question, how does the thing change? And two things which we are very interested in are acceleration and tension. So once we understand in these
Right.
three, we could actually scale it to any question. That is the beauty of these
All right.
examples. Okay.
Yeah.
Now,
Wait, so only two and three out of the three that you showed, only two and three use a pulley.
yes, we are using pulley for only two and
Um,
three. The first one
okay.
is the where external force is applied to move it, right? It's like, kids play
Okay.
with the toys and they just pull something and it
Pull
moves.
it. Yeah.
So those were the examples which we
Okay.
did
Yeah.
earlier. Now, let's look into
Right. Yeah.
where external force is there. Now, in this case, we have to look into a system one by one. So let's look into this particular section where the mass is hanging. Since M1 is hanging, it does have a weight, and this weight is a force which is pulling it down, correct? And the force is M1G. Now, since the system moves down with an acceleration of A, as shown here, right? Therefore,
Yeah.
you see that the net force is positive, right? Net force is not
Right.
zero in this case. What is the net force? Net force for us is the difference between the downward pull due to gravity on this mass and the tension in the string. The tension is always
Uh,
in the opposite direction. Therefore, we wrote
yeah.
an equation m1g minus ft. That is the net force. Now, this net force, according to the second law of Newton, should be equal to mass into acceleration. Mass
Yeah.
on acceleration is a, and so we get our first equation. Is that clear to you?
Yeah. That's clear.
And this is our free body diagram, which clearly indicates that we do have a mass m1, force downward is m1g, ft is the tension, a is the acceleration on this string.
Uh,
Correct?
yeah. Yeah.
We have seen that this string is inextensible, right? And this string will have a tension force, which is f of t, in the opposite direction. Because of the pulley, it will be transmitted to the other end of the string. Same value, correct? Because it has
Yeah.
negligible mass. It has
Right.
negligible mass. And same value, f of t, that tension pulls the second mass. And the acceleration remains same because the system is supposed to have a negligible mass, correct?
But
So, yes.
Sorry, the thing
I
that I
mean,
didn't get was,
yes,
yesterday when you explained me with the pulley and it having no mass, you said when you like pin it on the wall, let's say something like that in the center, it's
yeah.
not going to have any mass because the pin is like holding it. But in this case, since it's like almost hanging off the thing,
No, no,
where,
this pulley is in a place, it is like pegged
oh,
down.
fixed.
Yes, yes. Pulley is fixed to
Oh,
the table and the rope is going over the pulley.
all right. Okay.
So it's a similar
Okay. Yeah.
situation, right? So rope is going
Yeah.
over,
Yeah.
and therefore we have this Ft. So on the second mass, you can see very clearly there is external force Ft, and this external force causes the acceleration A, and therefore the equation will be Ft, the tension, is equal to m2a. So that becomes our
Mhm.
second equation.
Yeah.
So we got these two equations, and to get acceleration and tension Ft from these two equations, very simple. If I add these equations, Ft and Ft will cancel, and we'll get
Uh,
m1g equals to a times m1 plus m2, correct?
yeah.
And then all the things are known to us, the two masses, the gravitational force, acceleration will be equals to m1g divided by m1 plus m2, correct?
Plus M2. Yeah.
Once you know acceleration, you can find Ft because Ft
Just
is
have it in.
nothing but m2 times a. So just multiply by the second mass to get the force due to tension. Is that clear to you?
Yeah. So it's kind of like forming just two like simultaneous equations and then
Well,
working from there.
yeah.
Oh, okay.
Now here is what I was saying. I just typed out the whole solution. So what we discovered was due to m1, which is hanging, there is a force of gravity, and that is the external force.
Yeah.
M1g minus the tension is equals to M1a, where a is the acceleration. And this tension is applied to the second mass, which is on the table, which also moves with the acceleration a. So f of t is also equal to m2a. If I add the above two equations, in that case, what do we get? We get that m1g is basically equal to, let me write m1g here, because ft and ft will cancel, is equals to m1a plus m2a, or m1g is equals to m1 plus m2a. We have taken it common, right? And then we
Yeah.
divide by the sum of masses, and we get the acceleration, which is mass 1 divided by sum of the two masses into gravitation force. So that
Yeah.
gives a general formula to find acceleration in a system where one mass is hanging and the other one is on the table. Is that clear to you?
Oh. So okay, I know you have to like do it that way, but if I just went straight to the formula, is that
Yeah,
just so much easier then?
yeah, it
I
is.
understand it though. Yeah. Okay.
At the end, I'll give you a summary of the formula for all the three. Once you see all the three formula together, it'll make so much of sense for you. I'm telling you.
Yeah. All
Another
right.
point. Now, Ft, is m2 times a. So we'll just multiply the acceleration which we calculated with the mass of the second object, and we get our formula, product divided by sum times gravitational force. You see product sum divided by g.
Yeah. Yeah.
So F is mass
Oh.
into acceleration, right? Acceleration is
Yeah.
gravity. And the mass is like product and sum in this case.
Oh, I see.
Very
Yeah.
easy
Yeah.
to remember. And since you know F is ma, you could go back to A also, which is
Yeah.
m over m. You understand?
Mm-hmm. Yeah. Yeah.
So
Yeah. I
once
do.
you have all these formulas on your sheet and you look at them and try to understand, the concept will be absolutely clear. So with this, I think it's very clear how to do this, correct?
Yep.
Let me give some values to these two masses and let's actually calculate what is acceleration and what is the tension in the string. So what I've done here is that I've just extended this question and I'm saying let the mass m1 be 6.0 kg and mass m2 be 4.0 kg. So I know acceleration is this formula and tension is the other formula. We'll just substitute the values 4 and 6 in the formula and calculate with gravity as 9.81, right? So once you multiply,
Yep.
you get acceleration of 5.886. Now, what should be the significant figure for your answer?
Sorry, it was it kind of the Wi-Fi broke up.
Okay, so Now here, what I'm doing here is, whenever you work on these examples, you should know to what accuracy you have to write your answer. So
All
normally,
right.
if it's not mentioned, in that case, you
In the
should
question.
oh, yeah. But in this question, we
Yeah.
have written exactly what we are looking for. So we have said that it should be accurate to one decimal place, right?
Oh, yeah.
The
Yeah.
statement was not there. Then, I mean, you
How
should
would I know?
two significant figures.
Oh, okay. Yeah, you said, didn't you say yesterday with whatever values are given in the question, whatever significant figure is given in the question, if that is not stated, then you just do it in that one.
Yes, yes, that's what I
Oh,
said.
okay.
And
Yeah.
now in this case, we have said one decimal place. So round it to one decimal place.
Okay. Yeah.
5.89 as rounded to 5.9 meters per second square. And for tension, I just multiplied the acceleration with the other mass, m2, and got my answer as 23.54, rounded to one decimal place as 23.5 newtons.
All right. Yeah.
Units and accuracy is very important when you write your answers, right? That ensures
Yeah.
truth, correct? Now, let me take the second example. I mean, is this all absolutely clear to you?
Yes,
The
it is.
concept, right? Very good.
Yeah.
Now, let's take the second example. We'll hang both the masses on the pulley. So both are
All
hanging.
right.
The question is still the same. Can you please read the question?
Yeah. Two boxes with mass of M1 and M2 are attached at the end of a light inextensible string. The string passes over a fixed light pulley, as shown in the figure. Find a general expressions for acceleration of each box and the tension in the cord.
Simple as that. Basically, all the questions in your book are saying the same thing. They're writing
Oh,
the statement in a different way. There are two
okay.
passes. Either they're hanging with this pulley, or one pulley and one table, or both are on the table, right?
Okay.
That is it. So
Right.
once we do these examples, things become so simple. So clearly,
Mm.
in this case, one mass is more than the other, both are hanging, so there is an acceleration. M1 is greater than M2.
Yeah.
Let us assume this, right? So we'll draw a free body diagram. That is always the first thing to do. So if you look at the first mass, you know the gravitational force pulls it down, and that is your net force. That is the force downwards. The Ft is the tension, which is going upwards. Difference of these two is the net force, correct?
Yep.
So the net force, F net, let me write, sometimes we write F net or sigma F is m1g minus Ft.
F
That causes
T.
an acceleration of A, and therefore it is equal to m1a. So we get our
Oh,
equation for 1, exactly same as what we did earlier.
yeah.
Second mass
Mhm.
is, however, hanging. It is not on the table. Since it is hanging, it also has this mass m2g force acting downwards. Correct?
Yeah.
The tension is upwards and tension is taking it up. So we are putting this up as positive direction. So the net force here is Ft minus m2g. Acceleration is A, same, since the string is inextensible and it is
Mm.
very light string. So that is equal to
That's
m2.
clear.
So again, the same
Yeah.
equation. You can actually add these equations and these cancel, and you can now find what A is, correct? Once you find
Yeah.
A, you can find what Ft is, correct?
Yeah, I
That's
like
the
that.
process. So let's move
Oh,
on.
so yeah, it's the same process. You just need to be aware of what is actually happening, like in the diagram, because you know that you can't just write like we did before, force
Yes.
equals ma, because you can see this. It's not on a table. It's like hanging
Yes.
again. So there's gravity acting on it. So you have to you should be aware that something else has to like act on it. So you
Correct.
can't just write the same thing. Yeah, that makes
Correct.
sense. Yeah.
Correct. So I'd like you to, Emmy, read this kind of summary here. Read this part.
Okay. So system of equations. Boxes are moving in different directions, and so we will consider two systems.
Very
They
important.
will, all right,
We
yep,
are moving in different operations. You cannot treat everything as one system. In the
yeah.
first example, both were on the table. They were both moving in the same direction. We could have just clubbed both the masses together and written one equation. You remember that part?
Yeah.
Here, you cannot do it. They are moving in different directions. And therefore,
Oh.
yes. And so, once again, read this part.
Okay, so boxes are moving in different directions, and so we will consider two systems. Oh, so before it was working in one direction, so we can use it as one system. Oh,
Yes.
I get it. Yeah. they will have the same acceleration and tension because of flexible inextensible string and the light pulley. Oh, so these assumptions we made. Oh, okay.
Yes. Same equations which we discussed earlier on the first system, which is M1G minus the tension Ft is equal to M1A. And in the second case, Ft minus M2G is M2A. When we add the above equations, what do we get? The Ft and Ft part cancels, correct? So this cancels, and we get M1G minus M2G equals to M1A plus M2A, taking G common and A common, and then dividing, we get the expression for acceleration. Is that clear to you?
Yeah. Yeah.
So in this case, we have difference of the masses on the top divided by the sum times the gravity. Is that clear?
Yeah.
Now, we can substitute the value of A and find the tension. Let's go to the next page and see our calculations. So we just calculated that the acceleration is difference of masses divided by the sum of masses times the gravitational force. We also had these two equations with us, correct? And now, from the second equation, I can actually rearrange the second equation, correct? Taking, let me just go one by one. So M1G minus Ft is M1A, taking M2G on the right hand side, we get Ft, which is the tension force, is M2A plus M2G. Now substituting the value of A, which we just calculated, we can simplify. So both have G common. So I factored out G, right? And then wrote M1 minus M2 over M1 plus M2, right? Like, in fact, I've done the calculation here once again, and then, you know, just go straight from here to there, correct? So we have G common, right? So G is common, and plus 1. So you just simplify taking common denominator. And once you do that, you know, M2 and minus M2 and plus M2 cancel away. You get 2 times M1 in the numerator. So 2 times M1 times M2 in the numerator now with sum of the masses in the denominator times gravity. So that becomes the force of tension.
Yeah. So it's just the same as the other one, just that there's a 2 in the calculation on the numerator section.
You see there's 2 tensions F2 going up, 2 twice.
Yeah.
Twice. So the tension is doubles up because both are acting up. So it makes sense, correct? So you must have seen so much of correlation between the examples. So I thought, let me summarize. But before that, let me again take some values for M1 and M2 and calculate the result. So in this particular example, I'm saying let M1 be 6 kg, M2 be 4 kg. And then I'm saying, well, let's calculate. Now, I'm not writing anything for rounding. So what should be the answer rounded to?
So in the calculation, we're given it's to 1 significant figure?
Yes.
No, 2. 1? Yeah, it is 1 significant figure. So why is the question in?
It should be 50, so rounded to 50. Yeah.
50?
Yeah.
Oh. That's why I was confused, because I saw the 2 and I was like, oh, that's right. So then I was like,
Important, right? You got it. So if I don't write anything.
It's a good test on me.
1 significant figure. Just do simple calculations, which are shown here. Plug in 4 and 6. 4 and 6 also is a good number, right? Because 4 plus 6 is 10. So you just divide by 10. It's so simple. I'm taking values which are very simple to work with.
You're just trying to make me understand the concept. Yeah.
And then round this to 1 significant figure, which is 2, and round this to 1 significant figure, which is 50, right? Do you get the idea?
Yeah.
So not 47. 47 will be a wrong answer.
All right. Yeah. It's weird though, because even in the exam, even if you just miss Newton's, like 1 mark is gone. Don't do it to 2. If you do it to 1, like it's supposed to be 1, and you do it to 2 significant figures, mark gone. And that's the difference between a whole grade sometimes. So like you can't really afford for that. Yeah.
Got it?
Wow.
Very good.
Yeah,
so
got it.
It's very important to put in the values, check your answer, be careful why there was a difference in answer, look into the significant figures and then figure it out. This is something very critical to work with, right? After doing all the labor in solving the question, if you write the answer incorrectly, you lose so many marks.
Yeah, and it's pointless after that, because that was hard work.
So, I mean, here is the summary for you. So what we have done today is we have looked into these 3 types of examples, right? So the first
Oh,
one we took earlier, and it was the same question. There are two masses, m1 and m2. Situation is
yeah.
slightly different. We are only interested in finding the acceleration and the tension in the string, correct?
Right. Yeah.
All our assumptions were same. Flexible, light string, correct? That was our assumption. So in the first case, you found that external force was applied, and this external force was Fp.
Yeah.
And therefore, the acceleration was force divided by total mass, right? That is Newton's
Yeah.
second force divided by total mass. That is acceleration. In the second case, this force was not applied externally by you, but it was because of the gravity, correct?
Right. Yeah.
M1g. So you see the numerator is what? M1g. So this force
Hmm.
Fp is being replaced by M1g. Equation is same, divided by M1 and M2. You see that?
Uh, yeah. Yeah.
Because the force applied now, F of P, is M1g because of the gravity, this hanging object.
Right.
In the third case, again, it is mg, but the net mass effect is there are two different masses on the other side. So it is m
Right.
minus m2. You get the idea.
Yeah. And then you still multiply by g because gravity is still acting on it.
Correct. Divided by m1 plus m2. Done.
So whenever there's a pulley, can you
Hmm.
just say you have to, whenever there's a pulley, you have to be aware that gravity is acting on it?
Yeah, of
Can
course.
you say that on?
Yeah,
Yeah.
yeah.
Okay.
Because both the masses are just hanging, right? And the
Right.
gravity is acting
Yeah.
on both. So the net
Yeah.
effect is m1 minus m2. That is why they move.
Oh, right.
So all
Yeah.
the three formulas are actually the same. Fp is
Hmm.
the force being applied. Maybe you applied externally, or maybe because of the difference in masses.
Gravity. Oh, yeah. Yeah. Yeah.
So that force is in the numerator, F of P, and divided by all the sum of the masses.
Hmm. And that's the same for all of them. You're dividing by the
All the
sum
three.
of the masses.
All the three.
Oh,
Got it?
yeah. Yeah, I did. That's clear. So, but I think the key point that I didn't know before this lesson is because you really stressed it. You know where you said it, with especially with the pulley, because they're acting in opposite directions. You
Yes.
need to be aware of that. Whereas with the first one, they're acting in the same direction, and the second one, they're acting in the same direction. So you use that as one system. Whereas with the
Equal.
pulley, the last one, you have to use two systems.
Correct. Now let's talk about the tension. Tension
Hmm.
is M2A, right? The second mass we'll always consider, and if there are many, consider the last one. If I
Last one,
put
yeah.
10, consider the last one. It is so simple.
10th one.
The tension is same.
Yeah.
Tension is
Yeah.
same.
Yeah.
So it is same tension and same acceleration. Just consider the
And
last mass M2A. That is the general form.
that's working out. Yeah. Because
Yeah.
if you did the first one, you'll have to subtract the one pulling force from the tension.
Go to the last
Yeah.
one.
Yeah.
Correct.
Right.
You know
Okay.
what acceleration is because you calculate, multiply with the last mass. You get your formula. So here,
Right.
Fp times m2, you get your formula. Second case, m2a is my tension, correct? So,
Yep.
so what I did was, we have this acceleration m1, I just multiplied by m2, correct? M2 times
Yeah.
2. A, I know, right? And in the
Right.
third one, it is important to understand it is twice m1 and m2 because there are two strings and two tensions.
Mm-hmm. And that's logically makes sense. Yeah.
Correct. So if we have a system where we have four strings, I mean,
You times it by 4.
oh yeah, you got it.
Yeah. I get it. Yeah. Yeah. Because
So
there's four strings, four
there's
things
a
acting
system
on
which
it.
is called rack and pinion. So you
Oh,
have four strings in there.
all
So
right.
there are
I
four,
didn't know that was a thing.
yeah, yeah, yeah. So there are four strings, four tensions.
Oh,
Correct. So now you understand how easily we can solve all these questions based on Newton's second law of motion.
yes,
Yeah,
I do. You made that look so easy. Yeah, I was really like because you know when you look at first glance in the book, you're like, oh my God, I can't do that. It's like too complicated.
it
But
is.
then because you showed the relation between all three of these, and you said that this was the most, these three are basically the questions that they just keep rewording differently in my book. But
Yeah,
there's like 50 of them. But because the principle and the correlation between all three is the same,
correct.
it's a few tweaks here and there, and it's logical. It's nice and easy.
Nice.
So I like that. Yeah,
That is
even
how
with
you
something
should.
I haven't learned with the full one, I know. So yeah.
So that's it. And next time, actually, in the next class, we'll introduce to you the coefficient of friction. So in all these examples, we are
Okay.
avoiding friction, right?
Right.
Friction
Yeah.
is an additional force which is acting in the opposite direction, just as we are having tension in this particular case. We'll add friction to it, and then we'll do questions related to your next topic, which relates to coefficient of friction. Is that interesting?
Yes, yeah, it definitely is. Wait, so with friction, do they specify in the question, or because we always assume that there isn't any, but
Yeah.
when with questions where they say friction, is it
Yeah,
actually said in the
they will
question?
tell you mu is the friction and it is 0. Let's say 0.5. Friction
Oh,
is
okay.
always a constant number and it is between two surfaces. So depending on
Okay.
the surface, we have different friction constants. Coefficient of
Right.
friction, it is called. So we'll take that up in the next
Ah,
lesson, okay?
that sounds interesting. Okay. So
Great.
thank you so much, sir, for your help. I really enjoyed that, like especially that last slide. It's going to be a lifesaver.
Yeah,
Gonna
good.
remember that table when I go in the exam. That's really
Correct.
helpful. So thank you so much.
My
And
pleasure. Have a great weekend. Enjoy your day.
yes, you too, sir.
Thank you.
Bye,
Thank
sir.
you.
Thank you. Bye.